So, hello, everyone. As networks get faster and faster, we sometimes have the problem on how do I look at all the packets in my network if something goes wrong. Our next speaker is working at the Amsterdam Internet Exchange, and he's been working on some really cool device. He will present us now. So it's a pleasure for me to introduce Mr. Arjen Wijn.
Thank you. This presentation is made at the last minute during the network troubles, so please bear with me. And it's divided in three parts. An introduction part on what is an internet exchange, the place where I work, where I'm using this system or planning to use this system. Which problem needs to be solved by this system and the solution for that issue. I'm giving some real-life examples, which I hope I can interact with you. And then a solution which consists of a system that is not made for what we want to do with it. First, I'm going to tell a bit about what's an internet exchange, because even people that work in the internet industry sometimes don't have it right, in my opinion. And therefore I present this tier model, where you on the top you have tier 1 providers that are big companies with large networks that span a large part of this world, but not the entire part. There's no company that has a network all around the world. And tier 1 providers, in the definition of Bill Norton, are providers that can exchange traffic with each other only by peering. And peering means that they see each other as equal, and that they don't have to pay to exchange traffic. So if this ISP wants to send traffic to this ISP, it can over this link, and they don't have to pay for it. Smaller ISPs, like the ones you probably have an internet account with, are here at the bottom. And they have to reach the entire internet. And they do that via an upstream provider, in this case ISP E. And they have to pay a large amount of money for that, for this traffic that goes over this link. And all these smaller providers where you have your internet account, well, they are sort of close by to each other. So it makes sense that they exchange traffic with each other. And by just setting up a switch in the middle, like here, and connecting their BGP routers to that switch, they can exchange traffic. And by doing this, they offload traffic to their upstream provider, and for that, they save a large amount of money. And this is really a large money saver. And by this switch part, everybody that connects to this switch can exchange traffic with each other. They can peer with each other. They see each other as equal, and they usually don't pay for that traffic. They pay an amount of money to run that switch park for the internet exchange, but they usually don't pay money for the traffic. So, by connecting, everybody can talk to everybody, but that does not happen. Some people don't want to peer with each other. So, you don't have a full mesh of traffic exchange over an internet exchange, but some internet exchanges like the one I'm working for, it's quite common for people to peer with everybody that wants to peer with them. So, this switch park, this is what I'm babysitting in my life. That's there in the middle of all these providers that do all their own stuff. And they are really different. You have large providers with change management processes, and if you call them, you have to go to several layers before you get somebody who knows what you are talking about. And if you call another one, you hear his wife complaining and his kid screaming on the back. So these are very, very different cultures, and you can imagine that, yeah, if there is a problem between the connection, that you cannot really trust what one party is saying or what the other party is saying, because everybody has a different perception of the problem. And for that, we need to monitor the system. And monitoring can be done, and we do that by just plugging in a computer to the shared medium, to the place where everybody is connecting to, and look at the traffic that is being broadcasted, being flooded out of this switch. And that tells a lot. That tells really a lot already. And this is what we do all the time. And I'll give you an example of a problem that has been solved by this method. Well, not completely solved by this method, but for a great deal completely solved by this method. And on a Saturday, it's always on a Saturday, there was suddenly a huge amount of Ethernet multicast traffic coming out. Ethernet multicast traffic is flooded to all ports in the switch. And this was really huge. Even gigabit ports were saturated by this traffic, because the source of this was a 10 gig router. A 10 gig router that was sending Ethernet multicast to the shared medium. And by just looking at that packet, in the frame itself, there was typically IP unicast traffic. So this was really wrong. So the first idea is, this switch is wrong, right? We should close this switch, and we did. And that solved the problem. But was this really the problem? What do you think? Of course not. Just by looking at this broadcast traffic, you could see that just before this started, there was an ARP request. An ARP request that was not coming from a totally different router to a totally other different router. And this was that ARP request. I changed the source MAC address a bit and the IP addresses a bit, but this was it. And what is wrong with this? Can somebody tell?
All zeros of the target MAC address.
And that's normal. That's normal. The ARP request is from a router that is saying, hey, I want to contact this. Who is this? Who has the MAC address of this machine? Please? Source is different than the subnet. Sender. No. What is wrong with this? The 195.69.144.0/23, that's the ARM6 prefix. This was really true. Correct. Ethernet multicast is being recognized by the first bit in network order. If that's a 1, then it's Ethernet multicast. Then the switch knows, hey, if there's 1, I'm going to flood it all around. And apparently, this router from AS1 saw this address, and the implementation of this router followed the suggestion that is in the RFC that if you see a MAC address change, just change your ARP table. And the implementers of this router didn't think that somebody could send a multicast address there. Or it might even have been done by design. So, indeed, this 0 caused all these problems. So, then you think, the sender of this ARP packet, he is doing something wrong. He is making this multicast. And that is this router. So we were looking at this router. And then, well, you have to see, if that is really that router that is causing this problem. So the only way to do that is by looking at the traffic that is coming in. And we do that. And if there's a gigabit link, then it's technically not so much of a problem to look into that line. But yeah, it turned out that it wasn't this line. It turned out that there was packet corruption going on in our own equipment, flipping exactly this bit sometimes, causing trouble. So this guy was not to blame, this guy was not to blame, we were to blame. And this is an example of where you need monitoring in this internet exchange. So I'm here in the middle, and if somebody sends something with tuddle and it comes out as buddle over this line, or presumably over this line, I need to check it. And for that we need a monitor system that can look into the line. And it can either look here, or it has to look here, or it has to look at somewhere in the switch park. And, well, the switch park is all connected with 10 gigabit lines, multiple 10 gigabit lines. We now even bundle 8 10 gigabit lines to handle the traffic load. I'll give you another example of where we need monitoring, and this is also a real-life example. First, I'm going to give you a bit of the situation of how people connect. Routers are expensive devices, and then their interfaces are very expensive. So what do ISPs that want to save money? They don't connect that router directly, no, they connect a switch. And make one link to that router, and do VLANs over that link, which they can use to connect to their own network and to their transit provider. In this way, they save interfaces. With connecting a switch to another switch, where this switch is under another control management than this switch, is a potential really dangerous situation. Because switches, they just want to forward traffic, and they want to say, hey, I'm a switch, and they do all kinds of things wrong, and you need to configure them before you can do this. And not everybody does that. And it gets even worse. If two of these providers do this, and they say, hey, we are next to each other, let's offload some traffic from the internet exchange, because that port costs us money as well, you can see you have a potential loop here. And Ethernet does not have any loop prevention. Ethernet, when an Ethernet packet is going into a loop, it loops forever until you break it. There's no TTL like IP has that counts down to a number when it is being thrown away. So people do this, and this actually, especially when this all started in 2001, 2002, this brought our internet exchange down several times. Because sometimes people forget to do write mem, and the switch reboots, and it comes back in a state where it's not configured, or it's really looping, or it's even can loop behind that and sending packets into the shared medium with a high packet weight. That's bad. So we came up with a solution. We only allow one MAC address, because whatever you put in between our internet exchange and your router is up to you. But we only want to see the MAC address of your router. And if we don't see the MAC address of your router, we'll block it. And we can even close your port if you do that. But then, well, if somebody has a router there and it comes for some reason another MAC address there, we block it and we close the port. And we have a syslog message